differently from another coffee or from itself consecutively is a confounding factor when we're trying to look at a single isolated attribute. And so here it is, controls versus sample sizing. We chose to go with sample sizing because we were already doing it and it was more realistic in terms of what we were trying to get out of this study. So here are Tim's questions. I'll just pop them up quickly. Does water activity and moisture content affect the quality of coffee and how? And does water activity and moisture content affect the shelf life of coffee and how? These are the two big ones. There are 4 more. These are the ones where it's like, if the answer is no, then we're done with it because it's expensive and it's difficult to maintain the data collection. Is there an ideal moisture content or water activity for green coffee and why? What are the biggest challenges when measuring? And this one is actually pretty interesting too. How does water activity during drying and storage affect the quality prior to coffee being shipped? We've done three studies at Origin with drying and water activity. All 3 have been compromised horribly by what I just would call ineptitude. It's frustrating. Are there alternatives for small roasters to measure and monitor water activity and moisture content? So just keep these generally in mind. We're going to go through some water activity stuff. We're going to go through some data, and then we'll circle back to these questions as well. So what is water activity first? We're going to talk about moisture content just a little bit. Moisture content is just what it sounds like. It's the measure of quantity of water in a system or in a product. That's pretty simple. It's concerned with the total amount of water. If you're purchasing coffee and it has 11% moisture, you're purchasing 11% water. In any substance, moisture content at a cellular level can be more or less bound to that substance. If you think of 2 quantities of water that are identical, one soaked up in a sponge, one just in a cup, the water in a sponge is essentially more bound to that sponge. You're going to have a harder time dissipating that water than you are the water in a cup. This degree of boundness is what water activity is measuring. It gets very tricky to conceptualize this because we tend to think in terms of quantities. Water activity is an energy measure. It's qualitative, not quantitative. Okay? So technically, water activity is this ratio. It's water vapor pressure. The ratio of water vapor pressure over a substance to that over pure water. So pure water has got some water vapor pressure if you put it into a sealed chamber in the headspace. So does coffee beans, so does cornflakes, so does lentils, so does everything. If it has water in it, it has some water vapor pressure over the headspace. This is a little chart. This is what it looks like basically. This is just water. This is that P0, pure water, looks like that. The ratio then would be to plot another line representing some kind of substance. Practically speaking, it's the energy status of the water in the system, and this is where it starts to get important. Water is just water. It's just a medium. It doesn't do anything besides sit there unless it's unbound and is met with some stimulus. The amount of boundness, the amount of binding, is what is going to basically offer resistance to that stimulus for the water. Because of equilibrium. Water seeks equilibrium. It seeks to balance out. So if you have a bag of raisin bran, before very long the raisins get hard and the flakes get soft and mushy. The reason is that the water in the system is seeking equilibrium. Now, it's not the quantity of unbound water. The first thing that I went and did was I conceptualized it as some of the water in this coffee bean is bound, some of it is not bound, and water activity is the unbound portion. And the scientist that I was working with on this, an actual scientist, corrected me very gently, kindly. It is not the quantity of unbound water, it is it is a qualitative measure of all of the water in the system. So these are different measures of different things. A couple of ways you can think about it. You can think about it as moisture content as total versus degree of boundness. You can also sort of think about it as the difference between a medium and movement or potential for movement in that medium, almost like an inertia situation. Question would be, is there correlation of water activity and moisture content? And this is interesting. Interproduct correlation is very irregular. If you have two products with the exact same moisture content, you have no idea what the water activity is. Intraproduct correlation may be more regular. If you have two samples of oats, you can more or less get the moisture content and have an idea, ballpark, of where the water activity is. And we'll see more about that in coffee, because one of the things that remains a question is coffee just coffee, or is Pacamara, and Bourbon, and Robusto, is that all just coffee, or are those, is it an interproduct correlation or relationship, or is it an intraproduct? We don't really know for sure as regards water activity. Hence, here's an example. Rolled oats, 10% moisture content, 0.65. The water activity scale is just 0 to 1. 0.65 is relatively high end of in the middle. Dried fruit, for example, like raisins, 15 to 20%, but a lower water activity. Green coffee at 10% moisture is roughly, and there's some variance, but it's roughly going to give you a 0.52 water activity. Now you bump up to 14 to 15% moisture, right at the low end of dry fruit, and your water activity jumps all the way up, again, in a range to 0.7100. So considerably wider ranging just in green coffee. So how is it measured? Not exactly like that, but Decagon is the water activity, is the company that manufactures these machines that we've been using, and this is what they have to say about it. Basically, it's about putting a little sample into a sealed chamber, regulating the temperature, and shooting a little laser at a mirror in the headspace and measuring dew point temperature, running an algorithm and kicking out a number. That's water activity. And the most simple thing they can say about it is, in a sealed container, the relative humidity of the headspace will equalize with the water activity of the sample. So as the temperature stabilizes and becomes uniform, then you will start to see that vapor pressure equalize with the relative humidity. Relative humidity will equal water activity at that point. Now, how is water activity measured? Part 2. This is how we do it at Cafe Imports. We put the sample into the machine. That's the machine. That's the lever, and we switch it over to the read position. That's about it. Practically, readings can take a huge, there's wild variance in how long the readings take. It has to do with the temperature of the room, it has to do with the temperature of the coffee. If it sits in the sun for a moment, even if it's all sealed up and it gets warm, the machine will just start beeping and say the temperature's, the sample's too warm. If it's just under that, it won't complain, but it'll take 20 minutes to equalize the temperature and give you a reading. So if we're looking at roughly 100 coffees per week, and we're trying to get readings on all of them, when they start to take 20 minutes, that's a large time commitment to trying to collect this data. The machine is very, very sensitive. If you leave a coffee sample out overnight, it will drop massively in its water activity. It's basically ruined, which is of interest. If you have bags of coffee in your warehouse, don't let people set them out with the top open. We have that back in our warehouse all the time. Not in our warehouse, but in our little roasting playroom. People get coffees and roast them, and then just massively expensive coffee sitting out, giving off all their goodness to the air. So here we are, open bags. You have to take a lot of care with everything you do with these things. And honestly, it's a little bit of a hassle. Moisture content is much, much easier to measure than water activity is. It's faster, it's less expensive, and it's not such a hassle as these guys are. So wet hands, that's no. Food products, keep them away. Coffee dust, if you've got a bag of some kind of really shaffy, or not shaffy, but really silver skinny pulp natural coffee, and you've got that dust in the bag, and it's in your sample, and now it's in the little tray, that's going to contaminate the next one. You have to calibrate this with a couple of fluids every day. If you get a little drop of the fluid somewhere in the sample reading chamber, that's again no good. So history. This guy, William James Scott, he figured this all out back in 1953, so it's been around for a little while. And what he actually figured out was that it was water activity, not moisture content, that governs microbial proliferation in food. If you think back to those oats and the dried fruit example, with the dried fruit had high moisture content, low water activity. Rolled oats were the opposite. Low moisture content, high water activity. What was observed was that the oats would have molding problems that the dried fruit would not have. And the question is why? Why is that? There's way more water, there's way more moisture in the dried fruit, and yet it just didn't work out that way. There it is. So there's the question. And what he found out was that there was this thing called water activity. Now, if you increase the water activity of the dried fruits to 0.65, you're going to get the xerophilic molds, are just molds that are able to flourish in a low moisture environment, a low water activity environment. And not until you increase the water activity will you see that those things proliferating. Different foods with the same moisture can have very different water activity. We saw that already with the green coffee. And then these questions, is green coffee a single food, or is it actually more like different foods? Now, moisture migration. So William Scott said water activity is a determining mechanism for microbial growth, and so the question then is, well, why is that? Why not moisture content? Water activity is what is establishing the direction of moisture migration, and here's another way that you can think about the difference between the two. Moisture moves from equilibrium from high water activity to low. Another way that you can sort of think about this is to say moisture water activities to equilibrium from high to low. Okay, that makes sense, yeah? So we have the raisin and the bran flakes, the raisin bran, moderate water activity and low water activity, and of course the raisins get hard because the water is moving from the raisins, moderate water activity, to the bran flakes, low water activity. A more interesting example is a cupcake with frosting. The cake part of the cupcake has a low moisture content, high water activity, and it is reversed for the frosting. So if you take a cupcake, like your Hostess, right, or General Mills or something, and you're producing a cupcake for the grocery store, and you put it in a little plastic bag in a box, you would expect that the cake would get soggy and the frosting would dry out. In fact, it's the reverse because of